The universe is 13.8 billion years old. That number is not an estimate. It is not a rough approximation made by scientists who are doing their best with incomplete information. It is a measurement. It has been confirmed by multiple independent methods, cross-referenced against each other, checked, rechecked, and published in peer-reviewed literature by teams working on separate continents with separate instruments. 13.8 billion years. That is established, and yet, inside that universe there are stars that should not exist. Not stars that are unusual, not stars that are rare, stars that are, according to everything we currently understand about how stars form and how long they live, older than the universe itself. You're sitting in a room right now. The light around you is falling on ordinary surfaces. Your body is doing the 100 quiet things. It always does, without asking you. And somewhere in the sky above you, visible to the naked eye on a clear night, there is a star called Methuselah, catalogued as HD 140283, that our best measurements suggest is somewhere between 13.7 and 14.5 billion years old. The universe, again, is 13.8 billion years old. This is not a rounding error. This is not a misprint. This is the data. And it means one of three things. Our measurement of the star's age is wrong, our measurement of the universe's age is wrong, or something about the way we understand the relationship between those two numbers is fundamentally incomplete. Every one of those options has enormous consequences. None of them has been ruled out. If this is the kind of investigation that interests you, the kind where the more you know, the stranger things get, subscribe now, because we are just getting started. Before we can understand why this is a problem, you need to understand how we know what we know. This is not a detour. This is the foundation. Every complication in this story rests on it. Start with the universe itself. How do we know it is 13.8 billion years old? The answer begins in 1929 in a small office at the Mount Wilson Observatory in California, where an astronomer named Edwin Hubble was looking at the spectra of distant galaxies. A spectrum, if you have never encountered the word in this context, is what you get when you take the light from an object and spread it out by wavelength, the way a prism spreads white light into a rainbow. Different elements absorb and emit light at very specific wavelengths. Those wavelengths act like fingerprints. Hydrogen has a fingerprint, calcium has a fingerprint, iron has a fingerprint. You can look at the spectrum of a distant star and know without any ambiguity which elements are burning inside it. What Hubble noticed, and what would change everything, was that the spectral fingerprints of distant galaxies were shifted toward the red end of the spectrum, not for one galaxy, for all of them, and the further away the galaxy, the more it was shifted. This effect is called redshift, and its cause is the same reason a siren drops in pitch as an ambulance passes you and moves away. The sound waves are being stretched. The wavelengths lengthen. When light does the same thing, it moves toward the red. And galaxies are doing this because the space between us and them is expanding. The universe is getting bigger. All of it, in every direction simultaneously. Run that expansion backwards in time, the way you might rewind a film, and all of that space converges on a single point. That convergence is what we call the Big Bang. The moment when everything that now exists was compressed into something unimaginably small and hot, and then began expanding. If you know the current rate of expansion, and you know the physics that governs it, you can calculate how long ago that moment was. 13.8 billion years. But that calculation requires you to know the expansion rate precisely. And measuring the expansion rate is where the trouble lives. The expansion rate of the universe has a name. It is called the Hubble constant, and it has been at the center of one of the most significant unresolved disputes in modern cosmology for the better part of a decade. We will come back to it. But first, the stars. Measuring the age of a star is a different problem from measuring the age of the universe. It does not involve looking at expansion rates or the cosmic microwave background. It involves physics that is considerably more intimate, and in some ways, more reliable. Stars are not permanent things. They are engines, enormous nuclear furnaces that run on hydrogen, converting it to helium through fusion, releasing energy in the process. The energy they release is the light you see at night. The rate at which they burn their fuel is dictated by their mass. A massive star burns hot and fast and dies young, sometimes in only a few million years. A small star burns cool and slow and can persist for hundreds of billions of years. Our Sun, for reference, is a medium-sized star. It has been burning for about 4.6 billion years. It has roughly 5 billion years left before it swells into a red giant and consumes the inner planets. This is confirmed by models of stellar evolution that have been tested against thousands of observed stars across the galaxy. The models are not perfect, but they are accurate. Here is the tool that astronomers use to determine stellar age. When a star exhausts its hydrogen fuel, it leaves the main sequence, the stable band of temperature and luminosity where hydrogen-burning stars live, and evolves into a red giant. In a cluster of stars that all formed at the same time, the most massive stars do this first, then slightly less massive stars, then slightly less massive than that, and so on. The point at which stars are currently turning off the main sequence, called the main sequence turn-off, tells you the age of the cluster. The stars that have just turned off are the ones whose fuel supply has just run out. If you know how long a star of that mass takes to exhaust its fuel, you know how old the cluster is. This technique has been refined over decades. It is not guesswork. It is the application of well-understood nuclear physics to observed astronomical data. It has been used to date hundreds of globular clusters, spherical gatherings of tens of thousands to millions of stars that orbit the outer regions of galaxies. These clusters are among the oldest structures in the observable universe. Their ages consistently come out between 11 and 13.5 billion years. That number is important. Hold it. Now add to it the time it took the first stars to form after the Big Bang. You cannot form a star on day one of the universe. The early universe was a hot, uniform soup of hydrogen and helium plasma. It had to cool. It had to condense under gravity into clouds. Those clouds had to collapse. The process takes time. How much time? Roughly 100 to 400 million years for the very first stars. Possibly longer for the first star clusters. So the calculation looks like this. If globular clusters are up to 13.5 billion years old, and they formed at least 100 to 400 million years after the Big Bang, then the Big Bang must have happened at least 13.6 to 13.9 billion years ago. That is perfectly consistent with a universe age of 13.8 billion years. Until you look at certain individual stars, HD 140283. That is its catalogue designation, a string of numbers and letters that gives no indication of what makes it remarkable. Astronomers have taken to calling it the Methuselah star, after the biblical figure said to have lived for 969 years. The irony is that the biblical Methuselah was notable for being very old. The astronomical Methuselah is notable for being, depending on how you read the data, impossibly old. It is not a distant object. This is one of the things that makes it so interesting. Methuselah is close. It is roughly 190 light-years away, which in cosmic terms is essentially next door. It is visible with the naked eye from a dark location. It has been studied in detail. Its properties are well measured. Its chemical composition is known. Its distance is pinned down. And its age, derived from those well-measured properties using established stellar evolution models, comes out at around 14.46 billion years, with an uncertainty of roughly 800 million years. Let that number sit for a moment. 14.46 billion years, plus or minus 800 million years. the universe is 13.8 billion years old. Even accounting for the maximum uncertainty in the Methuselah measurement, shaving 800 million years off the best estimate, you still get 13.66 billion years, which is still older than the minimum plausible age of the universe when you account for star formation delay times. You can see why this attracted attention. The 2013 study that produced this result, led by Howard Bond at Pennsylvania State University, used data from the Hubble Space Telescope's fine guidance sensors to measure the star's parallax, the tiny apparent shift in its position as Earth orbits the Sun, with extraordinary precision. Parallax is the most direct method of measuring stellar distance that we have. It does not rely on models or assumptions, it is geometry. You measure the angle, you calculate the distance, it is established. The team was careful. They knew what the result implied. They spent considerable effort checking their work, revising the stellar model inputs, exploring every possible source of systematic error. The final age they published, 14.46 billion years, plus or minus 800 million, was after all of those corrections. The problem did not go away. What kind of star is Methuselah? It is what astronomers call a metal-poor subgiant. The word metal in astronomy means something different than it does in everyday conversation. To an astronomer, anything heavier than hydrogen and helium is a metal. Lithium, carbon, oxygen, iron, all metals, and Methuselah has almost none of them. Its iron abundance is less than 1,000th of the Sun's. It is made almost entirely of hydrogen and helium. This is a crucial detail. The very first stars in the universe, the population astronomers call population 3 stars, would have been made of almost pure hydrogen and helium. Because those were the only elements that existed before nuclear fusion, and stars began creating everything else. Methuselah is not quite that primordial. It has trace amounts of heavier elements, which means it formed from gas that had been slightly enriched by the deaths of even earlier stars. It is, in other words, at least a second-generation star. The universe had to exist long enough for a first generation of stars to live and die and scatter their material before Methuselah could form. That makes the timeline even tighter. The age of the universe is not measured directly. There is no cosmic clock you can consult. Instead, the age is derived from the expansion rate, the Hubble constant, combined with models of how matter energy and dark energy have influenced that expansion over time. If your expansion rate is right, your age is probably right. If your expansion rate is wrong, your age is wrong. And this is where things get genuinely uncomfortable. There are two main ways to measure the Hubble constant. They are completely independent of each other. They use completely different physical phenomena. They should give the same answer. They do not. The first method works in the early universe. Scientists use the cosmic microwave background, the faint glow of radiation left over from the Big Bang, detectable in every direction across the sky, as a kind of snapshot of what the universe looks like 380,000 years after it was born. The temperature variations in that snapshot encode an enormous amount of information about the early universe's composition and dynamics. By fitting a theoretical model to those temperature variations, scientists can extract the Hubble constant. This is the method used by the Planck satellite, which spent 4 years mapping the cosmic microwave background with exquisite precision. Planck's value, 67.4 kilometers per second per megaparsec, plus or minus 0.5. That sounds technical. Here is what it means in plain terms. For every 3.26 million light-years of distance between us and a galaxy, that galaxy is receding from us at an additional 67.4 kilometers per second. The further away something is, the faster it appears to move away. That rate, 67.4, is Planck's answer. The second method works in the local universe. Scientists use what they call the distance ladder, a chain of overlapping measurement techniques, each calibrated against the one before it. that allows us to measure distances to ever more remote galaxies. At the base of the ladder is parallax, which gives us accurate distances to nearby stars. On top of that sits a class of stars called Cepheid variables, which pulsate with periods directly related to their intrinsic brightness. On top of that sit Type 1a supernovae, which are thought to explode with a consistent brightness, making them useful as standard candles across vast distances. Chain these steps together, and you can measure distances to galaxies hundreds of millions of light years away. Then you compare those distances to the galaxy's redshifts, and you get the Hubble constant. The value from this local method, from teams led by Adam Rees at the Space Telescope Science Institute, 73 kilometers per second per megaparsec, plus or minus roughly 1.67.4 versus 73. The gap between those two numbers is called the Hubble tension, and it is not small. It is not a rounding difference. It is a discrepancy of roughly 8 to 9%, and the statistical significance has been steadily increasing as both measurements have become more precise. In 2019, the tension stood at about 4.4 sigma, meaning the probability that it was a statistical fluke was less than 1 in 1,000. In 2022 and 2023, with additional data from the James Webb Space Telescope, that significance climbed further. This matters for the age problem in a specific and painful way. If the local measurement is right, if the universe is expanding at 73 rather than 67.4, then the universe is younger than we thought. Running that faster expansion rate backwards in time gives you a younger universe. The current estimate of 13.8 billion years is derived from the Planck value. Using the local value, the age might be closer to 12.5 to 13 billion years. That makes the problem with Methuselah dramatically worse, not better. If the universe is 12.5 billion years old, a star that is 14 billion years old does not become slightly paradoxical. It becomes catastrophically paradoxical. It would require a star to have formed before the universe existed, which is, to be very direct about this, not possible. Something is wrong somewhere. The question is where. Let us walk through the possibilities carefully, not enthusiastically, carefully. Each one has evidence for and against it. None has been confirmed, none has been eliminated. The first possibility, the age of Methuselah, is wrong. The stellar models we use to date stars could have errors in them. The physics of stellar interiors involves processes that are extraordinarily complex: convection, diffusion, nuclear reaction rates, magnetic fields, the behavior of partially ionized plasma under extreme pressure. These are modeled numerically, and the models have assumptions baked into them. If any of those assumptions are off by the right amount in the right direction, the star could appear older than it actually is. Which assumptions matter most? The biggest lever is something called helium diffusion. In a star's outer envelope, heavier elements tend to sink over time under the influence of gravity, while lighter hydrogen rises. If helium sinks faster than the models predict, the observable surface composition changes in a way that can affect the age estimates. Some researchers have argued that including more accurate helium diffusion rates in the models reduces Methuselah's estimated age by several hundred million years. A few hundred million years helps. It does not solve the problem. The second possibility, the distance measurement, is wrong. Everything about stellar age estimation depends on knowing where the star is. The luminosity of a star, how intrinsically bright it is, can only be calculated if you know its distance. If Methuselah is slightly closer than we think, it is slightly less luminous than we think, which means it is slightly less evolved, which means it is slightly younger. The 2013 parallax measurement that anchored the current age estimate was the most precise measurement of Methuselah's distance ever made. But parallax measurements, even from the Hubble Space Telescope, have error bars. More recent work using the Gaia satellite, a European Space Agency mission that has measured the parallax of over 1 billion stars with unprecedented accuracy, has refined the distance estimate somewhat. The result nudged the age estimate down slightly, but not enough to close the gap. The third possibility, the oxygen abundance, is wrong. The chemical composition of Methuselah affects the stellar models in ways that are sensitive and complex. In particular, the oxygen-to-iron ratio turns out to be important. In the 2013 study, the team found that Methuselah has a higher oxygen-to-iron ratio than previously assumed. The star is actually somewhat more oxygen-rich than earlier studies had indicated. That higher oxygen abundance, plugged into the stellar models, pushes the age down. This is what brought the best estimate from around 16 billion years, where it was in the 1990s, down to 14.46 billion. The team was explicit about this. Each refinement of the chemical composition input moved the age estimate in the right direction, which suggests that further refinements might move it further still. Maybe. Or maybe the remaining uncertainty is smaller than the remaining discrepancy, and no amount of refinement will close the gap entirely. The fourth possibility, the universe is older than 13.8 billion years. This is the most radical option, and it requires you to conclude that there is something wrong with the standard model of cosmology, the lambda-CDM model, which currently describes the universe with extraordinary success across an enormous range of observations. But the Hubble tension itself is already suggesting that something may be wrong with that model, and some cosmologists have proposed specific modifications that would make the universe older. One proposal involves what is called early dark energy, a form of energy that would have been present in the early universe, behaving somewhat differently from the dark energy we observe today. The idea is that early dark energy would have altered the sound horizon, a specific length scale imprinted in the cosmic microwave background, in a way that would change how we interpret the Planck data. If early dark energy was real, the universe might be older, and the Planck-derived age of 13.8 billion years would need to be revised upward. This is not speculation. Papers proposing and testing this idea have been published in major journals. The idea remains contested. The data are not yet decisive, but it is being taken seriously by serious people. In December 2021, humanity launched the most powerful space telescope ever built, the James Webb Space Telescope, designed by NASA in partnership with the European and Canadian space agencies. Developed over 3 decades and billions of dollars, folded into a rocket like an origami miracle, and unfurled in the cold of space 1.5 million kilometers from Earth, was intended to see the first stars and galaxies that ever formed in the universe. It was designed to look at the universe's infancy. What it found was not supposed to be there. In its first year of science operations, as it pointed towards some of the most distant corners of the observable universe, it began detecting galaxies. Galaxies that, given their redshift, given how far the universe had expanded since their light was emitted, should be seen as they existed only a few 100 million years after the Big Bang. Galaxies at the very edge of what cosmologists expected to be observable, if anything existed at all that early. And those galaxies were wrong. Not wrong in that they did not exist, wrong in that they were too big, too bright, too structured, and too numerous. In the standard cosmological model, the early universe should be almost featureless at this stage. Structure, galaxies, clusters, filaments, takes time to assemble under gravity. You start with small fluctuations in density. Gravity amplifies those fluctuations. Gas collapses. Stars form. Stars cluster into galaxies. Galaxies merge and grow. This process, under the standard model, does not produce massive, well-formed galaxies a few 100 million years after the Big Bang. There simply has not been enough time for gravity to do that much work. And yet, the James Webb Space Telescope found them. Candidate galaxies, some since spectroscopically confirmed, sitting at redshifts corresponding to only 300 to 500 million years after the Big Bang, with stellar masses and star formation rates that should not be possible at those epochs under current theory. One galaxy, designated JADES-GS-Z13-0, was confirmed at a redshift of 13.2, meaning we are seeing it as it existed only about 320 million years after the Big Bang. At that epoch, the universe was not supposed to have had time to assemble something like this, but there it is, confirmed, measured, published. Another galaxy, reported in a 2023 paper and designated as a candidate extreme redshift object, has been proposed to sit at a redshift that would place it even earlier, at a time when the universe was perhaps only 200 million years old. If confirmed, it would be the earliest object ever observed, and its existence would be deeply difficult to reconcile with standard models of structure formation. What does this mean for the age problem? It means one of two things. Either the early universe was able to form massive structures far faster than our models predict, which would require new physics, new understanding of dark matter behavior, or new star formation efficiency mechanisms, or our understanding of cosmic time is wrong in some way we have not yet identified. Both options are serious. Both are being investigated. Neither has been resolved. Think of it this way. Imagine you're an archaeologist and you've established through multiple independent dating methods that a particular civilization in a particular region did not arise until 3,000 years ago. Then someone starts digging and finds elaborate temples, paved roads, and written language in strata that your best dating tools say are 6,000 years old. You would not simply discard everything you know, but you would not ignore the temples either. You would dig more carefully. You would question your assumptions. You would look for the error or for the new explanation. That is precisely where cosmology sits right now. Methuselah is not alone. It is the most individually famous example of the age problem, but it is not the only data point. Globular clusters, those ancient, dense spheres of stars that orbit the outer halos of galaxies, have been raising similar questions for decades. The oldest globular clusters in the Milky Way's halo have been dated to between 12.5 and 13.5 billion years old, depending on the cluster and the method. That range is consistent with the 13.8 billion year universe age, provided the clusters formed within the first few hundred million years after the Big Bang. And some of the oldest clusters do seem to have formed very early. Their chemical compositions suggest they are among the most primitive stellar populations known. But the uncertainties in these ages have been a persistent source of tension. In the late 1990s, before the expansion of the universe's acceleration was properly accounted for, some globular cluster age estimates came out at 16 to 18 billion years. That was a crisis. It meant the universe appeared to be younger than its oldest contents, which is logically impossible. The crisis was resolved partially when measurements confirmed that the universe's expansion was accelerating under the influence of dark energy, which made the age of the universe older than previously calculated. The globular cluster ages, combined with revised stellar models, fell into an uncomfortable but workable agreement with 13.8 billion years. Workable, not tight, not comfortable, workable. The oldest confirmed globular cluster ages sit right at the edge of what is permissible. NGC 6752 has been dated to around 13.4 billion years. NGC 6397 to around 13.4 billion years. 47 Tucanae, one of the most studied globular clusters in the sky, comes in at around 13.06 billion years. These numbers are consistent with the 13.8 billion year universe age, but they are consistent only if the clusters formed very quickly after the Big Bang, leaving a formation delay of only 300 to 400 million years. And now the James Webb Space Telescope is showing us that large structured objects can apparently form faster than we thought. If that is true, it might actually help some of the globular cluster ages make more sense. The clusters could have formed very early indeed. But it also means that the physics of early structure formation is not what we thought it was, which means we need to revise the formation delay estimates, which feeds back into everything. The pieces keep moving. In 1998, two independent teams of astronomers studying distant Type 1a supernovae made a discovery that would earn the Nobel Prize in Physics 14 years later. They found that the universe was not just expanding, it was expanding faster and faster over time. The expansion was accelerating. This required an explanation. The obvious candidate, gravity, should be slowing the expansion down, not speeding it up. Gravity pulls things together. For the expansion to be accelerating, something had to be pushing outward. Something with negative pressure. Something that did not dilute as the universe expanded the way matter does, but instead maintained its energy density. Something that, unlike matter, could push space itself apart. We have a name for this something. We call it dark energy. It constitutes roughly 68% of the total energy content of the universe. It is the dominant component, and we have essentially no idea what it is. In the standard cosmological model, dark energy is modeled as a cosmological constant, a fixed energy density woven into the fabric of space-time, the same everywhere and at all times. This is Einstein's famous lambda, the term he originally added to his equations and then called his greatest blunder, before the accelerating expansion was discovered, and it turned out to be necessary after all. Under this model, dark energy does not change. It was the same density yesterday, as it is today, as it'll be in 1 trillion years. But there is another possibility. Dark energy could be dynamic. It could change over time. It could have been stronger in the past and weaker now, or weaker in the past and stronger now. A dynamic dark energy would behave differently from a cosmological constant, and the difference would affect how we calculate the universe's expansion history and therefore its age. In 2024, results from the Dark Energy Spectroscopic Instrument, DESI, a massive survey based at the Kitt Peak National Observatory in Arizona that has measured the three-dimensional positions of tens of millions of galaxies, raised the possibility that dark energy may indeed be changing over time. The preliminary results were not conclusive. They were, in the language of the physicists who produced them, suggestive. The significance was that the 2.5 to 3 sigma level, enough to be interesting, not enough to be definitive. But if dark energy is evolving, it changes the expansion history of the universe, which changes the inferred age, which changes everything. This is what makes cosmology genuinely difficult. The age of the universe is not a single measurement that stands alone. It is a derived quantity that sits at the intersection of multiple other measurements. The expansion rate today, the expansion rate in the past, the composition of the universe, the behavior of dark energy. Pull on any one of those threads, and the age estimate shifts, sometimes in a way that helps the problem, sometimes in a way that deepens it. Here is a much stranger possibility. What if the laws of physics were not the same in the past as they are today? The question sounds like science fiction. It is not. There is a number called the fine structure constant that determines the strength of the electromagnetic force, the force responsible for light, for chemistry, for the behavior of electrons in atoms. Its value is approximately 1/137. It is dimensionless, meaning it does not depend on the units you use to measure it. It is the same whether you're measuring in feet or meters or light years. And for decades it has been assumed to be exactly that, a constant, fixed, unchanging, the same today as it was at the beginning of time. But several observational studies looking at the absorption spectra of quasars, ancient, intensely bright objects whose light has been travelling toward us for billions of years, have found hints that the fine structure constant may have had a slightly different value in the distant past. The evidence is contested. Different analyses of similar data have reached conflicting conclusions. The effect, if real, is tiny, at the level of parts per million, but a tiny change in the fine structure constant would change the rate of nuclear reactions inside stars. And a change in the rate of nuclear reactions inside stars would change how long stars live, which would change stellar age estimates, which would change the apparent ages of all the old stars we have been discussing. This is not a mainstream proposal. Most cosmologists do not think the fine structure constant has changed. The evidence is weak and disputed, but the fact that this is even being investigated at all tells you something about the state of the field. When the standard explanations are insufficient, physicists begin looking at things that were previously considered settled. The speed of light presents a similar, even more radical version of this question. There is a fringe of physicists, and it is a fringe, let's be clear, who have proposed that the speed of light was higher in the very early universe. A faster speed of light in the early universe would solve certain cosmological problems, including the so-called horizon problem, the fact that opposite ends of the observable universe, which have never been in causal contact with each other, have nearly identical temperatures. The standard solution to the horizon problem is called cosmic inflation, a period of exponentially fast expansion in the first tiny fraction of a second after the Big Bang. But a varying speed of light is an alternative. It remains highly speculative. The evidence for it is weak to non-existent, but it would, if true, change how we interpret almost everything, including the ages of stars and the universe itself. Most physicists will tell you this is not the answer. They are probably right. But the very existence of these discussions tells you something true. We are at a moment when the foundations are being examined, not because physicists enjoy instability, but because the data is pushing them there. There is a model that cosmologists have relied on for roughly 3 decades. It is called lambda CDM. Lambda for dark energy, CDM for cold dark matter. It describes a universe made of about 5% ordinary matter, the stuff you can touch and see, 27% dark matter, which we can detect only through its gravitational effects and have never directly observed, and 68% dark energy, which we understand even less. This model predicts the distribution of galaxies across the cosmos, the patterns in the cosmic microwave background, the abundances of light elements forged in the first minutes after the Big Bang, and the large-scale structure of the universe with astonishing fidelity. It is not a guess. It is a framework that has survived confrontation with data for 30 years. The Hubble tension does not automatically destroy it. The James Webb observations do not automatically destroy it. These are challenges that need to be taken seriously, but a model that explains 100 things correctly does not get discarded because 2 things don't fit yet. You investigate the 2 things, and that is what is happening. Across dozens of universities, observatories, and research institutes worldwide, people are investigating the 2 things. The Hubble tension has spawned an entire sub-industry of proposed solutions. Some of them modify early universe physics, early dark energy, primordial magnetic fields, neutrino interactions that change the sound horizon. Some of them modify late universe physics, a dark energy that changes over time, interactions between dark matter and dark energy. Some of them challenge the measurement chain itself, systematic errors in the Cepheid calibration, biases in the supernova sample. No proposed solution has succeeded in resolving the tension without creating problems elsewhere. That is important. It suggests the tension is real, not artifactual. Real tensions point to new physics. The James Webb observations of massive early galaxies have similarly generated a flood of proposed explanations. Maybe the initial mass function of stars in the early universe was different, weighted more toward massive, short-lived stars that exploded and recycled material quickly, accelerating the formation of new stars. Maybe dark matter in the early universe clumped differently than expected, creating denser seeds for galaxy formation. Maybe the feedback mechanisms that modern models use to limit star formation, supernova blasting gas out of galaxies, black holes heating surrounding material, were less efficient in the early universe. Each of these is a concrete, testable modification to existing physics. None has been confirmed. All are being worked on. The feeling in the field, and this is something that comes through clearly when you read the papers, not just the press releases, is that something genuine is happening. Not a crisis in the sense of the field being in chaos, a crisis in the sense of a doorway that has appeared in a wall that was supposed to be solid. People are standing in front of it, looking through. Dark matter is worth spending some time on, because it turns out to be more relevant to the age problem than it first appears. The existence of dark matter was first proposed seriously in the 1970s, based on the observation that galaxies rotate in ways that cannot be explained by the gravity of their visible matter alone. The outer regions of spiral galaxies rotate just as fast as the inner regions when they should be rotating more slowly. The only way to explain this within general relativity is to assume there is additional mass that we cannot see. That mass is dark matter. Subsequent evidence has accumulated from multiple independent sources. Gravitational lensing, the bending of light by massive objects, reveals dark matter halos around galaxies and clusters that are far more massive than the visible matter would predict. The large-scale structure of the universe, the cosmic web of filaments and voids within which galaxies are arranged, matches the predictions of a universe dominated by cold dark matter with extraordinary precision. The cosmic microwave background temperature fluctuations are consistent with dark matter having been present in the early universe and influencing the growth of structure from the very beginning. This is confirmed physics. It is not speculation, but what dark matter is at the particle level remains completely unknown. Dozens of candidates have been proposed. Weakly interacting massive particles, WIMPs, were for decades the leading candidate. They have not been detected in direct detection experiments, despite increasingly sensitive searches. Axions are another candidate, originally proposed to solve a problem in quantum chromodynamics. They have the right properties to be dark matter. They have not been detected either. Sterile neutrinos, primordial black holes, ultralight bosons. The candidate list is long, and the confirmed detections are zero. What does this have to do with the age of the universe? The connection is subtle but real. The behavior of dark matter, how it clumps, how it interacts with ordinary matter, how it evolves over time, is central to models of structure formation, which are in turn central to understanding how quickly galaxies and star clusters assembled in the early universe. If dark matter behaves differently from what the standard cold dark matter model assumes, the timescales of structure formation change. The age constraints from globular clusters depend on assumptions about when those clusters formed, which depends on structure formation, which depends on dark matter. Some researchers have proposed forms of dark matter that interact more strongly with themselves, self-interacting dark matter, or that have small but non-zero masses that affect their clustering behavior, warm dark matter. Both of these alternatives would change structure formation in the early universe in ways that might be consistent with the James Webb observations of massive early galaxies. Both remain unconfirmed. Both remain testable. The universe is a system. Pull on one part and something else moves. The age problem is not isolated. It is connected to the Hubble tension, to the James Webb early galaxy observations, to the nature of dark matter, to the behavior of dark energy, to the physics of stellar interiors, to the initial conditions of the Big Bang itself. Every one of these is an open thread, and all of them are being pulled at the same time by the same community. There is a phenomenon from the first 380,000 years of the universe that leaves its fingerprint on everything. It is called baryon acoustic oscillations, and it is one of the most beautiful things in cosmology. In the early universe, the plasma of matter and radiation was not uniform. There were tiny density fluctuations, regions that were slightly denser than average and regions that were slightly less dense. Gravity pulled matter toward the denser regions, but the radiation, photons, created enormous pressure that pushed back outward. The result was sound waves, waves of compression and rarefaction propagating through the plasma at a speed of roughly half the speed of light. The early universe was literally ringing. At 380,000 years after the Big Bang, the universe cooled to the point where electrons and protons could combine into neutral hydrogen. When that happened, an event called recombination, the plasma became transparent. The photons stopped interacting with matter and streamed freely outward. Those photons are what we detect today as the cosmic microwave background, and at the moment of recombination, the sound waves were frozen in place. The scale of those frozen waves, the distance that a sound wave had time to travel in 380,000 years before being frozen, is called the sound horizon. It is approximately 150 megaparsecs, or roughly 490 million light-years. This length scale is imprinted in the distribution of galaxies across the universe today. If you look at the positions of galaxies and measure how often pairs of galaxies are separated by roughly that distance, you find a small but statistically significant excess. Galaxies prefer to be separated by about 490 million light-years. This is the baryon acoustic oscillation signal. It is a ruler in space, a standard length scale that cosmologists can measure at different cosmic epochs to track how the universe has expanded over time. The baryon acoustic oscillation signal, combined with the cosmic microwave background and Type 1a supernovae, forms the bedrock of modern cosmological measurements. These three independent methods agree with each other, mostly. They all point to a universe age in the vicinity of 13 to 14 billion years. They all point to a universe made mostly of dark energy and dark matter. They all point to the same expansion history, and yet the Hubble tension persists. The local distance ladder, anchored in the nearby universe, gives a different expansion rate than the early universe methods. Both cannot be fully right. The sound horizon, if used as a standard ruler in both the early and late universe, should give consistent results. It does not quite. The inconsistency is small, but it is real, and it is pointing somewhere. One proposed resolution involves modifying the size of the sound horizon itself. If there was something in the early universe that slightly altered the speed of sound in the plasma, an early dark energy component, for example, or a new type of interaction, it would change the size of the sound horizon. That would change how we interpret the baryon acoustic oscillation signal. It would change the derived Hubble constant from early universe methods. It might bring the two measurements into agreement, or it might create new problems in other places. The work continues. It is worth stopping here to be precise about what is established and what is not. This is the kind of distinction that matters, and the kind that often gets lost in discussions of cosmological problems. Confirmed, the universe is expanding. This is measured directly in the redshifts of galaxies. It has been confirmed by multiple independent teams over nearly a century. Confirmed, the expansion is accelerating. This was measured in 1998 using Type 1a supernovae. It has been confirmed by baryon acoustic oscillations, the cosmic microwave background, and other independent observations. It earned the Nobel Prize in 2011. Confirmed. The cosmic microwave background exists, is consistent with a hot Big Bang origin, and carries the imprint of density fluctuations in the early universe. This has been measured by COBE, WMAP, and Planck with extraordinary precision. Confirmed. The oldest stars we have measured have ages in the range of 13 to 14.5 billion years, depending on the star and the method. The Methuselah star age of 14.46 plus or minus 0.8 billion years is a published peer-reviewed result from a team using Hubble Space Telescope data. Confirmed. There is a statistically significant discrepancy between the Hubble constant as measured from the early universe and the Hubble constant as measured from the local distance ladder. The significance of this discrepancy has been assessed at 4 to 5 sigma by multiple independent analyses. Confirmed, the James Webb Space Telescope has detected galaxies at redshifts corresponding to the first few 100 million years of the universe that have stellar masses and star formation rates inconsistent with standard structure formation models. Several of these have been spectroscopically confirmed. Not confirmed but seriously proposed: early dark energy, dynamic dark energy, modifications to the sound horizon, modifications to stellar interior physics, errors in the Cepheid calibration chain. None of these has been established. All are being actively investigated. Not confirmed, highly speculative, varying constants of nature, varying speed of light, alternative theories of gravity. These remain on the fringe of serious cosmological investigation. They are not impossible. They are not supported by strong evidence. This is where the field actually is. Not in chaos, not at the edge of abandoning the Big Bang. In a place of genuine, productive tension, where the data is being pushed hard enough that something new is starting to show through. The local measurement of the Hubble constant depends on a chain of measurement techniques, each calibrated against the one below it. This chain is called the cosmic distance ladder, and it deserves a closer look, because the question of whether there are errors somewhere in it is central to the Hubble tension. The first rung is parallax. For nearby stars, you can measure how much the star appears to shift against the background of distant stars as Earth moves around the Sun. Half the total shift, expressed as an angle, gives you the parallax. The distance is the inverse of the parallax in arcseconds. This gives you the distance in parsecs. 1 parsec is about 3.26 light-years. This is direct geometry. It requires no assumptions about the physics of the star. It is the most reliable distance measurement we have. The second rung is Cepheid variables. These are stars that pulsate. They expand and contract with a period that is directly related to their luminosity. Brighter Cepheids pulsate more slowly. This period luminosity relationship was discovered by Henrietta Swan Leavitt in 1912, working at the Harvard Observatory. She noticed it in Cepheids in the Small Magellanic Cloud, a satellite galaxy of the Milky Way. If you measure the period of a Cepheid, how long it takes to complete one pulsation cycle, you know its intrinsic luminosity. Compare that to its apparent brightness, and you have the distance. Cepheids can be seen out to distances of tens of millions of light-years. They are calibrated using the Cepheids in the Milky Way and in nearby galaxies whose distances are measured by parallax. The third rung is Type 1a supernovae. These are explosions that occur when a white dwarf, the collapsed remnant of a dead star, accretes matter from a companion and exceeds a critical mass, triggering a thermonuclear explosion. These explosions are thought to be standard candles. They all have approximately the same intrinsic brightness, and with correction for certain observable properties of the light curve, that brightness can be pinned down precisely. Type 1a supernovae are visible across billions of light-years. They extend the distance ladder to cosmological scales far beyond where Cepheids can be seen. The Hubble tension lives the relationship between these rungs. The Cepheids in galaxies where supernovae have also been observed are used to calibrate the supernova brightness. If there is a systematic error in the Cepheid distances, if Cepheids in high metallicity environments behave differently from Cepheids in the Milky Way, or if there is a crowding bias from unresolved background stars, the calibration is off. That error propagates to the supernova distances, and from there to the Hubble constant. Adam Rees and his team have spent years looking for such errors. The James Webb Space Telescope was used specifically to check the Hubble Space Telescope's Cepheid measurements. The concern was that the Hubble telescope's infrared detector might be blending light from crowded stellar fields, making Cepheids appear brighter than they are, which would make their distances appear smaller, which would bias the Hubble constant upward. The James Webb measurements found some crowding bias in the Hubble data, but not enough to close the Hubble tension. The 2023 paper reporting these results concluded that systematic errors in the Cepheid measurements could account for only a small fraction of the discrepancy. The tension remained. The rungs of the distance ladder have been checked. The tension is not going away. Something real is causing it. Stellar ages are not the only independent check on the age of the universe. There are other chronometers, other independent clocks built into the physics of the cosmos, that tell us something about how old things are. One of them is radioactive decay. Certain radioactive elements produced in stellar explosions and distributed into the gas from which new stars and planets form decay at known rates. Uranium-238 decays into lead-206 with a half-life of about 4.47 billion years. Thorium-232 decays into lead-208 with a half-life of about 14.05 billion years. By measuring the current ratio of these isotopes in the oldest stars using high-resolution spectroscopy to detect the faint absorption lines of these elements in ancient stellar spectra, you can, in principle, calculate how long ago those elements were formed. This technique is called nucleochronometry, and it has been applied to a handful of extremely old, metal-poor stars, where both thorium and uranium lines can be detected. The results are consistent with stellar ages in the range of 12 to 14 billion years, depending on the star and the assumed initial abundance ratios. The method is less precise than main sequence turn-off dating. The initial abundance ratios are uncertain, but it provides an independent line of evidence that the oldest stars are genuinely old. Not as old as some stellar model ages suggest at the high end, but old, very old. Another chronometer is white dwarf cooling. White dwarf, the dense cooling remnants of dead stars, cool at a predictable rate. The coolest, faintest white dwarfs in a star cluster are the oldest. By measuring the temperature of the coolest white dwarfs in globular clusters and comparing them to cooling models, you can estimate the age of the cluster. This is completely independent of main sequence turn-off dating. It uses completely different physics, and it gives similar answers. The oldest globular clusters come out at 12 to 13 billion years. Multiple independent chronometers, multiple independent methods, all pointing to the same uncomfortable range. The oldest stars are right at the edge of what a 13.8 billion year universe can accommodate. Methuselah, with its central estimate of 14.46 billion years, is right at the edge of being outside it entirely. The fact that every method agrees on the age range does not mean every method is right. There could be a systematic error common to all of them. Something about the way we understand stellar interiors, something about the physics of white dwarf cooling, something about the nuclear decay rates we have measured in laboratories. But common systematic errors across completely different physical processes would be deeply surprising. When multiple independent methods give similar answers, that convergence is itself a form of evidence. There is a deeper problem underneath all of this. A problem so severe that some physicists consider it the worst unsolved problem in theoretical physics. And it connects directly to everything we have been discussing. The cosmological constant, the lambda in lambda CDM, the mathematical representation of dark energy, has a measured value. It is small, extraordinarily small. The energy density of dark energy is approximately 10 to the power of minus 29 grams per cubic centimeter. That is almost nothing. A volume of space the size of your living room contains about as much dark energy as a few hydrogen atoms worth of mass energy. Now here is the problem. Quantum field theory, the most precisely tested physical theory in history, predicts that the vacuum of space should be seething with energy. Virtual particle pairs constantly popping into and out of existence, contributing to the energy density of empty space. When you calculate how much vacuum energy quantum field theory predicts, you get a number that is approximately 10 to the power of 120 times larger than the observed value of dark energy. 10 to the power of 120. Not 10 times larger, not a million times larger. 1 followed by 120 zeros times larger. This is called the cosmological constant problem, and it is not a small discrepancy to be explained away. It is the largest discrepancy between theory and observation in the history of physics. The observed value of the cosmological constant is not just small, it is small in a way that requires a cancellation of essentially perfect precision between the positive contributions of quantum vacuum energy and some negative contribution that we do not understand and cannot derive from first principles. Why does this matter for the age of the universe? Because if we do not understand why the cosmological constant has the value it has, we do not fully understand the dynamics of the universe's expansion. And if we do not fully understand the dynamics of the expansion, our age calculation, which depends on integrating those dynamics back through time, has an unknown error somewhere in it. This does not mean the 13.8 billion year age is wrong. The age calculation has been tested against so many independent observations that a large error seems implausible. But a small error, enough to move the age by a few 100 million years in either direction, cannot be ruled out on the basis of the cosmological constant problem alone. The age problem might be a small crack in a structure that is otherwise sound, or it might be a small crack that is connected to a fundamental flaw in the foundation. The work is to find out which. Science does not move through argument alone, it moves through data, and the next decade will deliver an unprecedented quantity of it. The Vera C. Rubin Observatory, situated on a mountaintop in northern Chile, will begin its Legacy Survey of Space and Time, LSST, in the mid-2020s. It will image the entire accessible southern sky every few nights, for 10 years, building up a dataset of extraordinary depth. Over the course of the survey, it will detect approximately 17 billion astronomical objects. Among them will be hundreds of thousands of Type 1a supernova, millions of Cepheid variables, and thousands of gravitational lensing events. The precision of the resulting cosmological measurements will dwarf anything currently available. The Euclid satellite, launched in 2023 by the European Space Agency, will map the three-dimensional distribution of galaxies out to redshifts of about 2. Meaning it will probe the universe as it existed when it was roughly 3 billion years old. It will measure baryon acoustic oscillations and weak gravitational lensing with enough precision to distinguish between the cosmological constant and various models of dynamic dark energy. If dark energy is evolving, Euclid will see it. The Nancy Grace Roman Space Telescope, formerly known as WFIRST, will survey the sky in infrared light, providing a wide-field infrared complement to the James Webb Space Telescope's deep narrow-field imaging. It will measure the distances and shapes of hundreds of millions of galaxies, providing exquisite constraints on the growth of cosmic structure over time. The James Webb Space Telescope itself will continue to probe the earliest epochs of the universe, finding and characterizing galaxies at redshifts beyond what current surveys have reached. The question of whether massive galaxies at very high redshifts are truly inconsistent with standard models, or whether revised models of star formation and feedback can explain them, will be settled or significantly constrained by Webb's observations over the next decade. The Gaia satellite, which has already revolutionized stellar astronomy with its billion-star astrometric catalogue, will release further data products in the coming years. Its measurements of stellar parallaxes and proper motions will refine the distances to Cepheid variables and improve the first rung of the distance ladder. If there are systematic errors in the Cepheid calibration, Gaia is the instrument most likely to find them. And there are gravitational wave observatories, LIGO and Virgo, and in the future LISA, the Laser Interferometer Space Antenna, a space-based gravitational wave detector that ESA aims to launch in the 2030s, offer a completely independent method of measuring the Hubble constant. When two neutron stars merge and produce both gravitational waves and an electromagnetic counterpart, the gravitational wave signal gives you the distance directly. The redshift of the host galaxy gives you the recession velocity. Divide one by the other, and you have the Hubble constant, with no distance ladder, no Cepheids, no supernova. This method is called the standard siren method. The current measurement from a small number of events is consistent with both the early universe and local universe values. The error bars are still too large to distinguish, but as more events accumulate, the statistical power will grow. By the end of the decade, standard sirens may be able to discriminate between the two values at the level of a few percent. The next decade will be the most data-rich in the history of cosmology. The Hubble tension will either be resolved or confirmed as genuine new physics. The early galaxy observations from James Webb will either be explained within the standard model or will require a fundamental revision of structure formation theory. The age of Methuselah will either be revised downward as stellar models improve or will stand as a genuine anomaly that demands a universe older than 13.8 billion years. These are not abstract possibilities, they are specific questions that specific instruments will address with specific data. We are close to knowing. Before we reach the end of this investigation, it is worth pausing on a question that sits underneath all the measurements. What does it mean to say the universe has an age? Time in general relativity is not a universal background tick. It is not a river flowing at the same rate everywhere, against which events can be measured. Time is woven into the fabric of space-time, and it runs at different rates depending on the gravitational field you are in and the speed at which you're moving. A clock at sea level runs very slightly slower than a clock on top of a mountain. The difference is tiny, nanoseconds per day, but it is real, and the GPS system that helps you navigate accounts for it explicitly. Without the correction, GPS would drift by kilometers per day. When cosmologists talk about the age of the universe, they mean something very specific. The time elapsed since the Big Bang, as measured by a hypothetical clock that has been at rest relative to the cosmic expansion since the beginning. This is called cosmic time, or co-moving time. It is not the time that you or any particular clock has experienced. It is the time of the universe as a whole, as defined by the expansion itself. This is a real and meaningful definition, but it depends on the Big Bang having a specific, definable moment of origin, and the Big Bang itself, the singularity, the point of infinite density and temperature, is a place where general relativity breaks down. The equations cannot be trusted arbitrarily close to that moment. Quantum gravity is needed, and quantum gravity is still an unsolved problem. We do not have a theory of what happened at the very first instant of the universe, and without that theory, the concept of cosmic time has a fuzzy beginning. This is not a reason to doubt the 13.8 billion year figure. In the regime where we can trust the equations, from about 10 to the minus 36 seconds onward, the age calculation is reliable. The fuzziness at the very beginning affects the age by far less than our measurement uncertainties. But it is a reminder that the age of the universe is a concept with a precise technical meaning, and that meaning has limits. Some cosmologists have proposed models in which the universe did not have a singular beginning. In the Hartle-Hawking no-boundary proposal, the universe has no defined beginning in time. Time itself becomes a dimension like space at the quantum scale, and before the Big Bang is a question as meaningless as north of the North Pole. In various bouncing cosmology models, the Big Bang was a transition from a previous contracting phase, and the universe is effectively infinitely old in both directions. In eternal inflation, our universe is a bubble that nucleated within a larger inflating spacetime that may itself have existed for an infinite time. If the universe did not have a finite beginning, the question "what is the age of the universe?" may not have a well-defined answer, and a star that appears older than 13.8 billion years might simply be revealing the inadequacy of the question rather than a measurement error. This is speculative. It is not the mainstream position. The mainstream position is that the universe had a beginning. The beginning was approximately 13.8 billion years ago, and the age problem is a real problem that needs a mundane physical explanation. But the speculative possibilities are worth knowing because they illustrate how deep the rabbit hole goes. The age of the universe is not just a number, it is a question about the nature of time itself. There is something specific that happens when you spend time with a problem like this. Not dismay, not the particular anxiety that comes from personal uncertainty, from not knowing whether you made the right decision or whether things will work out. Something quieter and different. The recognition that the universe contains structure we have not found yet. That the map and the territory do not fully match. Most people have no sense of this. The age of the universe feels, from the outside, like settled knowledge. 13.8 billion years. You have seen the number. You probably learned it in school or encountered it in a documentary. It sits in the category of things that are known. And most of it is. The number is good. The evidence is strong. But it is not perfect. And the imperfection matters because that is where the next thing lives. Every significant discovery in the history of science has lived in a discrepancy. Not in the confirmed center of what was known, but in the gap between what the theory predicted and what the measurement found. The orbit of Mercury did not quite fit Newtonian gravity, and that gap led to general relativity. The black body spectrum of thermal radiation did not quite fit classical physics, and that gap led to quantum mechanics. The expansion of the universe was not decelerating as it should have been, and that gap led to the discovery of dark energy. The discrepancies are not embarrassments, they are the leading edge. Methuselah might be the leading edge of something. The Hubble tension might be the leading edge of something. The James Webb early galaxies might be the leading edge of something. They might all be the leading edge of the same thing, a modification to the standard cosmological model that we've not yet identified, a piece of physics that we are about to discover. Or they might not be. The stellar models might be corrected. The Cepheid calibration might have a systematic error that someone identifies next year. The early galaxies might turn out to be explained by modified star formation efficiency. Methuselah's age might come down to 13.4 billion years, with the next generation of parallax data and revised opacity tables. These are real possibilities. The history of cosmology contains many apparent anomalies that turned out to be measurement errors. The scientific process cannot tell you in advance which of these outcomes will occur. It can only tell you what to measure next, what instrument to build, what assumption to test, and then you measure and build and test and see. There is another constraint on the age of the universe that operates completely independently of stellar ages and expansion rates. It involves the lightest elements in existence: hydrogen, helium, and lithium, and the 3 minutes that followed the Big Bang. In the first 3 minutes of the universe, temperatures and densities were high enough for nuclear fusion. Protons and neutrons collided and fused, producing helium nuclei, trace amounts of lithium, and a small amount of deuterium, a heavy isotope of hydrogen, with 1 proton and 1 neutron. This process is called Big Bang nucleosynthesis, and it is one of the most precisely understood chapters in the history of the universe. The predictions are specific and testable. Big Bang nucleosynthesis predicts that the universe, after those first minutes of fusion, should be made of roughly 75% hydrogen and 25% helium by mass, with trace amounts of deuterium and lithium-7. These predictions are tested directly by measuring the primordial abundances of these elements in the oldest, most chemically unprocessed objects in the universe: ancient, metal-poor gas clouds and extremely old dwarf galaxies that have not been contaminated by stellar nucleosynthesis products from later generations of stars. The helium abundance matches the prediction well. The deuterium abundance matches beautifully. But lithium is a problem. the observed lithium-7 abundance in the most ancient metal-poor stars is consistently lower than Big Bang nucleosynthesis predicts, by a factor of about 3. This is called the cosmological lithium problem, and it has been around for decades without resolution. The stars might have destroyed their surface lithium through internal mixing processes. The nuclear reaction rates used in the nucleosynthesis calculations might have small errors that compound over the timescales involved. There might be new physics in the early universe, some decay process or resonance not yet incorporated into the models that reduced lithium-7 production. No explanation has been confirmed. All remain in play. The lithium problem is relevant to the age question because it points at the same region of concern, the physics of the very early universe. Big Bang nucleosynthesis occurred in the first 3 minutes. Stellar ages are anchored in physics that played out over billions of years. The Hubble tension involves the expansion history over the full 13.8 billion year span. And yet all 3 anomalies, lithium, stellar ages, Hubble tension, converge on the same uncomfortable suggestion. The early universe may have contained physics not fully captured by current models. Multiple anomalies pointing in the same direction across completely different physical processes and completely different measurement techniques have historically been a reliable indicator that new physics is waiting to be found. The history of science contains these moments. The anomalies that preceded quantum mechanics were multiple and diverse: blackbody radiation, the photoelectric effect, atomic spectra. None of them individually was considered a fatal problem for classical physics. Taken together, they were telling a single story. We do not know whether the current anomalies in cosmology are telling a single story, but the possibility cannot be dismissed. We use the word billion casually in this context. A billion years. The universe is 13.8 billion years old. The star is 14.46 billion years old. The difference is roughly 660 million years, perhaps less when uncertainties are applied favorably. These numbers seem comparable in the abstract. They are stated in the same units. They sit in the same paragraph. They are not comparable in any sense that a human being can directly experience. The difference between them, 660 million years, is more than the entire span of complex animal life on Earth. 660 million years ago, on this planet, there were no land animals, no forests, no insects, no fish with jaws. The Cambrian explosion, the extraordinary diversification of animal body plans that underlies all subsequent animal evolution, including the lineage that eventually produced you, was still roughly 70 million years in the future. Every vertebrate species that has ever existed, from the first jawless fish to every dinosaur to every mammal to you, has arisen within the last 540 million years. And in the context of the age of the universe, 660 million years is barely 5%. It is the kind of margin that, in everyday affairs, you might round away. In cosmology, you cannot. Because 5%, when threaded through the equations of stellar evolution and cosmic expansion, means the difference between a star that formed before the universe existed and a star that formed within a comfortable margin after it. The precision the field demands is extraordinary. The fact that it has been achieved is more extraordinary still. Consider what it took to arrive at this level of measurement. Telescopes that can resolve the parallax of a star 190 light-years away, an angular displacement smaller than the apparent width of a human hair seen from a kilometre away. Spectrographs that can detect the abundance of specific elements in starlight at parts per million, precision from photons that have been travelling for 190 years. Stellar evolution codes that incorporate nuclear physics, fluid dynamics, radiative transfer, and convection into coherent numerical models of entire stellar lifetimes running to billions of years. Cosmological models that combine general relativity, quantum field theory, particle physics, and observational data from satellites and ground-based observatories into a consistent picture of 13.8 billion years of cosmic history. All of these tools exist, all were built in the last century. Most of the precision we are discussing was achieved in the last 3 decades. In the context of a 14 billion year old universe, 3 decades is nothing. It is 0.000000002% of cosmic time. In the context of human science, it is everything. The speed of progress in cosmological measurement over the last generation has no historical precedent. The fact that we have become precise enough to notice the discrepancy between Methuselah and the universe is, in one sense, its own kind of triumph. We did not have to confront this problem. We could have been living with uncertainties large enough to make the tension invisible. Instead, the measurements got good enough to reveal it. That is how progress works. You sharpen the tools until the problems that were hidden become visible. Then you work on the problems. There is a particular quality to the uncertainty that surrounds the age problem. It is not the manufactured uncertainty of those who dispute well-established findings for ideological reasons. It is not the false humility of saying, science never really knows anything. It is something more specific and more honest, the discomfort of being at a genuine frontier, where the tools are good, the data is real, the analysis is careful, and the answer is still not settled. This is different from how uncertainty gets portrayed in most public discussions of science. When scientific findings are reported, the uncertainty is usually either erased, a single confident number is given without error bars, or weaponized. Someone uses the existence of uncertainty to argue that no conclusions can be trusted. Neither approach captures what is actually happening. What is happening is that a community of thousands of researchers working on overlapping problems with complementary instruments is progressively narrowing the space of possible answers. With each new measurement, the acceptable possibilities shrink. With each new telescope, the frontier moves. The Hubble tension in 2019 was measured at 4.4 sigma. By some analyses, in 2023, it reached 5 sigma. It is not dissolving under pressure from better data, it is sharpening. That is the signature of a genuine anomaly. Under scrutiny, it holds. An artifact collapses when you look more carefully. A real discrepancy becomes clearer. The James Webb Space Telescope's early galaxy observations initially raised the concern that some candidates might be lower redshift imposters, galaxies whose colors mimicked very distant objects. Some candidates did turn out to be closer than initially estimated. This is how the process works. Candidates are proposed, then tested, and the ones that fail are discarded. But a significant number of the high redshift galaxy candidates survived spectroscopic confirmation. Their redshifts are measured, not inferred from color alone. They sit definitively in the first few 100 million years of cosmic history. They are more massive than the standard model predicts. They have held up under the most rigorous available scrutiny. The anomaly holds. This does not mean the standard cosmological model is about to be overturned. Established scientific frameworks are extended and refined far more often than they are replaced. General relativity extended Newtonian gravity into regimes where Newtonian gravity failed, without discarding it elsewhere. Quantum mechanics extended classical mechanics into regimes of atomic scale and energy quantization, without making classical mechanics wrong at human scales. Lambda CDM will almost certainly be extended rather than replaced. Dark energy will turn out to be something more complex than a pure cosmological constant. Dark matter will turn out to have additional properties that affect early structure formation. The sound horizon will turn out to be slightly different from current calculations once early universe physics is better modeled. And Methuselah will probably turn out to be slightly younger than the current best estimate once stellar models are updated with better opacity calculations and more accurate treatments of atomic diffusion. That is the most likely resolution to the most famous single data point in the age problem. But the broader cluster of tensions, Hubble early galaxies, globular cluster ages, lithium, may require something genuinely new. Science does not know in advance which outcome it is heading toward. That is not a bug in the system. That is the system. On the 14th of September 2015, two L-shaped instruments in Louisiana and Washington state, the LIGO detectors, each with arms 4 kilometers long, capable of measuring a distance change smaller than 1,000th the diameter of a proton, registered a signal, a ripple in space-time. The vibration lasted less than a second. When the data was analyzed, it corresponded to two black holes, each roughly 30 times the mass of the Sun, spiraling together and merging 1.3 billion light-years away. The event had released more energy in the fraction of a second of the merger than all the stars in the observable universe emitting light in the same moment, and we detected it as a displacement in space smaller than any measurement ever made by any instrument in human history. This was gravitational wave astronomy. It opened a new window on the universe, and it offered something that cosmologists had been hoping for, an independent way to measure the Hubble constant. Here is why. When two neutron stars merge, not black holes but neutron stars, which are dense enough to produce a characteristic electromagnetic counterpart, the gravitational wave signal carries within it a precise measurement of the distance to the merger. The amplitude of the gravitational wave decreases with distance in a known way. Measure the amplitude and you have the distance directly from first principles with no distance ladder required. No Cepheids, no Type 1 supernovae, no chain of calibrations that might introduce systematic errors, just geometry and general relativity. In August 2017, LIGO and the European Virgo detector detected the gravitational waves from a neutron star merger. The event was designated GW170817. Within 2 seconds, a gamma-ray burst was detected by the Fermi Space Telescope from the same direction. Within hours, dozens of observatories across the world and in space had trained their instruments on the aftermath, watching the kilonova, the radioactive glow of heavy elements freshly forged by the collision, fade over days and weeks. This single event confirmed that neutron star mergers are responsible for producing gold, platinum, and most of the other heavy elements beyond iron in the periodic table. The gold in any ring you're wearing was almost certainly produced in a collision like this billions of years ago. From the gravitational wave amplitude, the team measured the distance to GW170817 directly. From the recession velocity of the host galaxy, NGC 4993, they extracted a Hubble constant. The value, 70 kilometers per second per megaparsec, with an uncertainty of +12 and -8. That central value sits between the Planck value of 67.4 and the local distance ladder value of 73. It is consistent with both within the uncertainties. The error bars are still too large to discriminate, but the error bars will shrink. Each new neutron star merger event gives another measurement. 10 events might give a Hubble constant measurement with an uncertainty of a few percent. 50 events would be competitive with the Cepheid and supernova measurements. 100 events would be definitive. The rate of detected gravitational wave events has been increasing rapidly as the detectors are upgraded. The third observing run of LIGO and Virgo detected nearly 100 candidate events. The fourth observing run, which began in 2023 with improved sensitivity, will detect more. The space-based LISA detector, if it launches in the early 2030s as planned, will detect thousands of events per year, including mergers of supermassive black holes at cosmological distances. This is why the Hubble tension may be resolved within the next decade, not because one side of the argument will capitulate, but because a third, independent measurement, requiring no shared assumptions with either of the existing two, will tell us which answer is right. If gravitational wave standard sirens converge on 67.4, the local distance ladder has a systematic error somewhere. If they converge on 73, the early universe physics needs revision. If they converge somewhere in between, the situation is more complicated and more interesting. Whatever the answer, the data will provide it. And when the Hubble tension is resolved, the age of the universe will be revised accordingly. If the universe is expanding faster than Planck says, it is younger. If it is expanding at 67.4, as Planck says, it is 13.8 billion years old, and Methuselah remains an uncomfortable anomaly that the stellar models need to account for. Every piece of this puzzle is connected to every other piece. Pull one thread and the whole web moves. The gravitational wave detectors are not the only new clocks being brought to bear. The Square Kilometre Array, an enormous radio telescope being constructed across South Africa and Australia, with a collecting area that will eventually total 1 square kilometre, will detect thousands of pulsars with extraordinary precision. Pulsars are rotating neutron stars that emit beams of radio waves with a regularity that rivals atomic clocks. By monitoring an array of pulsars distributed across the galaxy, astronomers can detect the gravitational wave background, the low-frequency hum of gravitational waves produced by the mergers of supermassive black holes throughout cosmic history. This pulsar timing array method provides yet another independent measure of the universe's gravitational history, constraining the expansion rate, the matter content, and the nature of dark energy. The first hints of this background signal were reported in 2023 by pulsar timing array collaborations in North America, Europe, India, China, and Australia, simultaneously, independently, and consistently. The signal is real. Its full characterization will take years. When complete, it will add another data point to the most important set of measurements in modern cosmology. Methuselah is 190 light-years away. On the scale of the galaxy, that is nothing. The Milky Way is 100,000 light-years across. On the scale of the observable universe, it is less than a rounding error. And yet the light that left that star 190 years ago and is reaching your eye tonight, if you are in the right hemisphere, if you know where to look, if the sky's dark enough, was emitted by an object that formed in the earliest epoch of the universe, before the Earth existed, before the Sun existed, before the Milky Way had taken its current shape, before most of the chemical elements we are made of had been forged in stellar furnaces and scattered into space. The star was already billions of years old before the first amino acids assembled in the early oceans of Earth. It was already billions of years old when the first multicellular organisms evolved. It was already billions of years old when the first humans looked up at the same patch of sky and felt whatever it is that humans feel when they look up at a sky they cannot explain. And we, in the span of a few thousand years of civilization and a few hundred years of systematic science, have developed the instruments and the mathematics and the physical understanding to look at that star and measure its age, to understand what it is made of, to know with uncertainty bars that are smaller than 10% how old it is, and to notice carefully, precisely, without alarm, that its age does not quite fit the universe we think we live in. That is not a failure. That is what success looks like at the frontier. The question is sharply posed. The tools to answer it are being built. The people to use those tools are alive right now, working in offices and on mountaintops and in data analysis pipelines, checking each other's work, arguing about systematic errors, proposing new models, discarding the ones that do not fit. You are inside this investigation, not as a passive observer, not as someone waiting for the result to arrive in a headline. You are a contemporary of the people doing this work. The universe is holding an anomaly, a thing that does not quite add up, a star that should not be there in the way it is there. And the species examining it is the same one you belong to. The universe is 13.8 billion years old. That is the best number we have. It is derived from converging independent measurements, and it is consistent with an enormous body of observed data across a vast range of cosmic epochs. It is not going to be dramatically wrong. The next revision, if there is one, will be measured in hundreds of millions of years, not billions. The Big Bang happened. The universe has been expanding and evolving since that moment. On these foundational points, there is no serious scientific dispute. And yet a star 190 light-years away appears to be 14.46 billion years old. That discrepancy, sitting at the 1 to 2 sigma level, when the full range of uncertainties is applied most favourably, is real. It has not been explained away. The 2013 measurement that produced the current best estimate was made with the best available instrument. The subsequent Gaia measurements refined the distance without closing the gap. The stellar models have been improved in the years since the result was published, and the improvements moved the age estimate downward, but not enough. It may be resolved by better stellar models. The physics of stellar interiors involves approximations that have been refined progressively over decades, and each refinement tends to push the oldest star ages slightly lower. Better opacity tables, more accurate treatments of helium diffusion, improved nuclear reaction rate measurements from laboratory experiments. All of these are ongoing efforts that will continue to sharpen the input parameters. At some point, the combination of better inputs and better distance measurements may move Methuselah's age below the age of the universe, and the problem will dissolve. This is the most likely single outcome, but it has not happened yet. And while we are waiting for it to happen or not happen, the Hubble tension sits unresolved at 5 sigma. The James Webb Space Telescope has found massive structured galaxies in the first few 100 million years of cosmic history that standard models of structure formation struggle to explain. The cosmological lithium problem remains unsolved. The pulsar timing array collaborations have detected what appears to be a gravitational wave background with properties that may carry information about the early universe. All of these threads are live. All of them are being followed by active researchers with funded programs and dedicated instruments. The Vera Rubin Observatory will see its first light. Euclid is already in space and collecting data. The Roman Space Telescope is in development. Gravitational wave standard sirens will accumulate toward the point of statistical significance. Gaia will release its final astrometric catalogue. Stellar models will be refined. The Methuselah star will be reobserved with the next generation of spectrographs, and its chemical composition will be measured with precision that was not possible when the 2013 study was conducted. The globular cluster ages will be revised. The Hubble tension will either close or confirm itself as new physics within this decade. We will know things within 10 years that we do not know now. Not all things. Not the deepest questions like what dark energy actually is at the fundamental level, why the cosmological constant has the value it has, what happened in the first instant of the universe before the physics we know was applicable. Those questions are harder. They may take longer. They may require theoretical breakthroughs that cannot be scheduled. But the specific tension between the age of the oldest stars and the age of the universe, that tension has the structure of a solvable problem. The pieces are in play. The instruments are either already in orbit or under construction. The community of researchers is the largest and best equipped it has ever been. You are living through a moment in the history of cosmology that will be remembered, not because we have all the answers, but because we are at the point where the questions have become sharp enough to have answers. The ambiguity is shrinking, the territories being mapped in detail, and the places where the map does not match the territory are becoming visible for the first time. Somewhere in the sky above you tonight, if the sky is dark enough, Methuselah is there, a point of light roughly 190 light-years away, visible with the naked eye from the right location on Earth on a clear night. A star made almost entirely of hydrogen and helium, with trace amounts of heavier elements that mark it as at least a second-generation object, formed from gas enriched by the death of even earlier stars that no longer exist and have left no direct trace. It is moving through the outer halo of the Milky Way, on an orbit it has traced for billions of years. It was old before your sun condensed from a cloud of gas and dust. It was old before the first complex animals appeared in Earth's oceans. It will still be burning, slowly, long after our sun has exhausted its own hydrogen and swelled and collapsed. The light leaving it right now will reach Earth in 190 years. The people who will detect that light do not exist yet. Their great-grandparents may not exist yet. And the instruments they will use, the spectrographs, the parallax satellites, the gravitational wave detectors, will probably answer questions we have not yet thought to ask. The universe is very old. Our understanding of it is very young, and that gap between the two, between the age of the cosmos and the age of our knowledge of it, is where everything interesting lives. The universe may be older than we think, or we may be measuring a star slightly wrong, or the physics of the early universe may be stranger than our models have captured. One of these is true, perhaps more than one. The investigation is not over. The tools are getting sharper. The people are paying attention. And we are the species doing the asking. A species that has existed for 300,000 years on a planet that formed 4.6 billion years ago inside a universe that is perhaps 13.8 billion years old, possibly slightly more, possibly slightly less. A species that looked up and measured and found something that did not quite fit, and then went back to work. And yet a star 190 light-years away appears to be 14.46 billion years old. That discrepancy at the 1 to 2 sigma level, depending on how you account for uncertainties, is real. It has not been explained away. It may be resolved by better stellar models, by better parallax data, by revised chemical abundance measurements, or it may be telling us something about the expansion history of the universe that we have not yet understood. The Hubble tension is real. Two methods of measuring the universe's expansion rate give different answers at the 4 to 5 sigma level. This is not a small discrepancy that will quietly disappear. It requires an explanation. If the local measurement is right and the expansion rate is higher than the early universe measurement suggests, the universe is younger than 13.8 billion years. That makes the stellar age problem dramatically worse. If the early universe measurement is right, something is wrong with the local distance ladder in a way that multiple teams using the James Webb Space Telescope have not yet found. Either way, something needs to give. The James Webb Space Telescope has found galaxies in the early universe that are more massive and more structured than standard models predict. This is confirmed by spectroscopic follow-up. It is not artifact. These galaxies formed fast, perhaps faster than the physics of gravity and gas dynamics should allow. This means either the physics of early galaxy formation is different from what we modelled, or the early universe was different from what we modelled, or both. These three problems are not identical. They may have separate explanations, but the fact that they are all pointing in the same direction, all suggesting that the universe may have been different in its early epochs than the standard model assumes, is striking. Scientists are trained to be cautious about patterns that emerge from multiple puzzles pointing in the same direction. It is possible to read connections into coincidences, but when the pattern is persistent, when it is found by independent teams using independent data, when it survives the addition of new and better observations rather than dissolving under them, it begins to look less like coincidence and more like signal. The Vera Rubin Observatory will see its first light. Euclid is already in space and collecting data. The Roman Space Telescope will launch. Gravitational wave standard sirens will accumulate. Gaia will release its final astrometric catalogue. Stellar models will be refined with better opacity calculations and updated nuclear reaction rates. The Methuselah star will be observed with the next generation of spectrographs, and its chemical composition will be pinned down more precisely. The globular cluster ages will be revised. The Hubble tension will either close or widen. We will know things within a decade that we do not know now. Not everything. Not the deepest questions about what dark energy is, or why the cosmological constant has the value it has, or what happened in the first instant of the universe. Those questions are harder, and they may take longer. But the specific tension between the age of the stars and the age of the universe, that tension will have a resolution. It already has the structure of a solvable problem. The pieces are in play. The instruments are either in orbit or under construction. And somewhere in the sky above you tonight, if the sky is dark enough, Methuselah is there. A pinprick of ancient light that has been falling through space since before your world existed, still burning slowly on the long tail of its hydrogen supply, still moving through the halo of the galaxy, tracing an orbit that began before the Earth was formed. A relic, a witness, an anomaly. The universe may be older than we think, or we may be measuring a star wrong, or the physics of the early universe may be stranger than our models assume. One of these is true, perhaps more than one. The investigation is ongoing. The tools are getting sharper. The question is well posed, and we are the species doing the asking.